In the last video, we saw control NOT gate or C NOT gate. In the similar fashion, we can create any control gate using a unitary matrix U, which is called as controlled U gate. This is a natural extension of C NOT gate. This diagram represents the circuit of controlled U gate. Instead of this unitary matrix, we can take any of our quantum gates like X, Z, H, etc. Let's see the working of this control U gate. If the control qubit is 0, then nothing happens to the target qubit. But if the control qubit is 1, then our gate U is applied to the target qubit. For example, if our matrix is the Z gate, then for the control qubit 1, the target qubit will be operated by the Z gate. In the last video, we saw multiple qubit state and how to renormalize them post measurement. Now we will see an important 2 qubit state called the Bell state or EPR pair, where EPR stands for Einstein, Podolsky and Rosen. Let's see one of the Bell state given by 0011 divided by root 2. The Bell state has the property that upon measuring the first qubit, one obtains two results, that is 0 with probability half, which implies that our post measurement state will be 0 0, and the second result is 1 with probability half, which implies our post measurement state will be 1 1, which implies that the measurement of the second qubit always gives the same result as the measurement of the first qubit. This implies that our measurement outcomes are correlated. Now let's see the generalized equation describing all the four Bell state, which is given by this equation. So for beta 0 0, where x is equal to 0 and y equal to 0, it would be beta 0 0 equal to 0, y is 0 plus minus 1 raised to x, and x is 0, so minus 1 raised to 0 would be 1 only. So our second state would be 1, and y bar, that is complement of y, which will be 1 divided by root 2. So this is the one of the state. Let's name this state as phi plus. So similarly, we can calculate all the remaining state using this general formula. Now, in order to realize these states, we can use a simple quantum circuit given below, which has an Hadamard gate and a C0 gate. So with the help of these circuit, we can verify the output of these Bell states. So for example, let's take the working of the circuit for the state psi plus, or for the input of beta 01, which should give us the output 01 plus 10 divided by root 2. So here our x is equal to 0 and y is equal to 1. So x is 0 and y is 1. So let's break the circuit in three parts: the first step, the second step and the third step. So in the first step, our state is 0 1, and the first qubit, that is 0, is operated by the Hadamard gate, and this state can be written as 0 1, where the 0 state would be operated by the Hadamard gate, which implies, so we all know when h operates on 0, we get 0 plus 1 divided by root 2 into 1. Now when we take this 1 inside, we have 0 1 plus 1 1 divided by root 2. So for our second step, our state is this. So this state would be operated by a C0 gate, which implies 0 1 plus 1 1 by root 2. When operated by C0 gate, we'll have in this third step the output as, when the control bit is 0, the target bit is left alone. So it would be 0 1. But when the control bit is 1, the target bit is flipped. So this will be 1 0 divided by root 2. So in the third step, that is where we get the output for B, x is 0, y is 1, 0 1, our output state is 0 1 plus 1 0 divided by root 2. In the similar fashion, you can check the output for any of the remaining state using this simple quantum circuit. Now let's see an important theorem called as the no cloning theorem, which says that there is no unitary operator that can clone any arbitrary qubits or quantum states. That is, it is not possible to make a copy of an unknown quantum state. So let's try to prove it. Suppose we have a unitary operator U that can clone a quantum state. That is, for our input state psi, it will make two copies of psi in the output. But since we need two inputs for two output for an unitary operation, let's assume the second input to be S. So this operation can be realized by a tensor product equation given by when U operates on psi tensor product S, we will get psi tensor product psi. One thing to note is that we can write the tensor product in terms of inner product or ket notation. That is, psi tensor product S can be written as psi S or psi S. It's one and the same. Now let's say we have two pure states psi and phi on which our unitary operator which can clone is copying them on the state S. So we will have two equations. That is, when our operator works on psi to copy the state on S, it will give us psi tensor product S. Similarly, when our operator works on phi, it copies this state on S, giving phi tensor product phi. Now let's take the inner product of these two equations, which implies phi tensor product S U dagger U phi tensor product S will be equal to RHS, which is psi tensor product psi into phi tensor product phi. Now as we all know the property of unitary operators, that is U dagger U is I. So this will become 1, which implies psi tensor product S tensor product phi. Here I have just flipped these two states since our tensor product are commutative, that is A tensor product B will be B tensor product A. This will be equal to psi tensor product psi phi tensor product phi. Now using this notation we can write this as psi S phi, which would be equal to psi and phi phi. Now this SS would be equal to 1 since it is the same state. So finally we'll have psi phi equal to this psi phi and this psi phi. We'll have psi phi the whole square. Now this equation implies that psi and phi can have only two results, that is either 0 or 1. When psi and phi is equal to 0, they are orthogonal, and when they are equal to 1, they are equal. That means we cannot clone an unknown quantum state or any arbitrary state. In order to clone a state, they must either be equal or orthogonal. So this was the proof of our no cloning theorem.